Okay, today we have to talk about acid-base titrations, and you've already done two. Friday you'll do the third. A titration is a gradual addition of an acid to a base until neutralization is complete. What neutralization? An acid plus a base yields salt and water. Okay, this is the neutralization. Now, Tom, do not go in front of the camera. Go that way. Now, we're going to talk about a number of different titrations. What's very important for you to know is the equivalence point. At the equivalence point, the moles of the acid equals the moles of the base. Right now, circle that because it's incredibly important. All right. Now, we use something called an indicator, and an indicator tells us the end point. Let's look at this graph. All right. This graph shows the titration of a strong acid with a strong base. How did I know it was a strong acid?
Because
the initial pH was very low. Okay. And I added gradually more and more NaOH until I hit this portion of the curve. You notice this portion of the curve, the pH is slightly changing, and then it has a huge meteoric rise in pH. If you look at this very small volume, very small run in X, there's a huge rise in Y. The equivalence point is equal to the when the moles of acid equals the moles of base. When you have a strong acid and a strong base, the pH at the equivalence point is always 7. Look, this is how this works. If we had HCl plus NaOH, those are both strong, right? It's going to make NaCl plus H2O. At the equivalence point, there's no more hydrochloric acid, there's no more sodium hydroxide, there's only NaCl and water. What is the pH of water?
7.
What is the pH of this salt? 7. Therefore, at the equivalence point, the pH of a strong acid titrated with a strong base will always be 7. So far, so good? All right, we pick an indicator so that it has a color change right in the place where the equivalence point happens. In fact, do you remember in the titrations that you did, all it took was 1 drop for the color to change and change the pH, the endpoint, yeah? We picked it for a reason. This is a titration curve. You plot the pH versus the volume of acid or base needed. I want you to look at the burettes that we have set up for Friday. Each one of these little gradations is what volume? 1 milliliter. I do not have a burette that measures volume in liters. It would be enormous, wouldn't it?
Yeah.
Can't find. Okay. Therefore, it's hard to work with, and I'm not going to lie, I'm talking smack about you right now. On the last test we had, there was an answer that I think it was this.
Yes.
All right, and you needed 3 significant figures to report it out, and I can't tell you how many people told me this, for which I took points off. So, because you're not good at remembering leading zeros aren't significant, I suggest we use a different molarity. It's the molarity that's equal to millimoles divided by milliliters. It is the same thing. However, I won't lose your precision when you make errors in your sig figs. So, strong acid, strong base. You know the net ionic for strong acid, strong base neutralization gives this, yes? Okay, if, when all is said and done, you have the hydrogen ions equal the hydroxide ions, the solution is neutral. If you have the millimoles of hydrogen ions are greater, then it's acidic. If the millimoles of hydrogen ions are less, then it's a basic solution. Okay. Now, we're going to go ahead and do a series of calculations. People like to ask you questions. What is the pH at this point during the titration? How about this point? How about that point? Over here, over there. All of these start with the same basic premise. There are 2 steps involved in doing a pH problem. The first one I made up all by myself. I call it an ICN step. It's the neutralization. After you've determined the neutralization step, you can find the pH using the negative log of either the hydrogen ion concentration or the hydroxide ion concentration. Depends which one is in excess. I just made it up, hang on. Okay, so here is our sampled titration problem. What's the pH at each of the following points in the titration of 25 milliliters of 0.1 molar hydrochloric acid by 0.1 molar NaOH? What do you know about these 2 acids and bases?
Strong.
So we know this is strong versus strong. Okay. So we're ready to go ahead and do the neutralization portion of this. Oh, not yet. It says, what's the pH before you add any NaOH? That would be this point on your titration graph.
1.
pH is equal to the negative log of the hydrogen ion concentration. You have 0.1 molar HCl. You know if you have 0.1 molar HCl, what you actually have is 0.1 molar hydrogen ions and 0.1 molar chlorine ions. The hydrogen ions are the only ones that affect the pH, so the pH is equal to the negative log of 0.1, which is 1. All right, that was easy. Now, what happens to the pH after the addition of 24 milliliters of 0.1 molar NaOH? Well, we need to do 2 things before we do this. First of all, write yourself a note. ICN must be in moles. You cannot do a neutralization problem in molarity. So we need to find the number of moles of what we're working with. So for our acid, we're going to use molarity is equal to millimoles over milliliters, and we're going to change that up a little bit. So the millimoles is the molarity times the number of milliliters. So our molarity is 0.1. Our volume is 25 milliliters. So we have 2.5 millimoles. Our base, we have 0.1 molar times 24 milliliters is 2.4 millimoles. Where are we on this curve? Have we hit the equivalence point?
No.
Nope, we're right about here-ish. So let's start our neutralization. We have the hydrogen ions. They mix with the hydroxide ions, and water is formed. Initially, we have 2.5 millimoles of the hydrogen ion. We have 2.4 millimoles of the hydroxide ion, and we have no water. The change at neutralization will be this. The limiting reactant will run out. Which one's the limiting reactant? OH. We will use all of our limiting reactant, and the OH will take the same number of millimoles of H plus to form the same numbers of millimoles of water. So at neutralization, we have 0.1 millimole of the hydrogen ions, we have no hydroxide ions, and we have 2.4 millimoles of water. The water isn't going to affect the pH, so we're just going to ignore it. Now remember that pH is equal to the negative log of the hydrogen ion concentration. What do these brackets mean? Molarity. I need to find molarity here. Molarity is equal to 0.1 millimoles over the entire volume of the solution. The entire volume of the solution is the 25 milliliters of acid, and the 24 milliliters of the base is 49. 49 milliliters. When I do some math, I figure out that my concentration is 0.00204 molar. My pH is equal to 2.69. Yes, Tom?
How do you know the volume does not change during the reaction?
I know how much base I add and how much acid I add.
Yeah, but how do you know the volume does not change?
Oh,
during the
it's
reaction?
considered to be additive. There will be a little change in volume, but not enough to make a difference in the pH. Remember, a jump in pH is a huge jump in the hydrogen ion concentration, so it doesn't really matter. Okay, at the equivalence point, pH is equal to 7. Don't be fooled. Why would you be fooled? Because you try to go ahead and calculate and do everything and just drive yourself sideways. Could you calculate it? Yes. What will you come up with? 7. Do you have to calculate it?
No.
Don't be a chump. What?
If it's 7, then like you're still hydrogen ion in there.
No, there are not. Because the pH at the equivalence point means the number of moles of this are equal to the number of moles of that. In our neutralization, this would be 2.5, or this would be 2.5, so there would be none, and I would just have 2.5 millimoles of water. The pH of water is 7. Okay, now take my advice. I've done these before. I'm even writing this in another color. Always start from the beginning. Nobody even knows what that means. Pretend like like nobody asked you the preceding questions.
Oh.
Like this is just one question out of sequence. Otherwise, you're going to make a mistake. That's all there is to it. Okay, after the addition of 26 mils of 0.1 molar NaOH. Well, 26 milliliters of NaOH, the number of millimoles, is equal to 2.6. All right, starting my ICN, the neutralization, the hydrogen ion plus the hydroxide ion yields water. Initially, I have 2.5 millimoles of the hydrogen ion. This time I have 2.6 millimoles of the hydroxide ion. I have no water. The change that will occur is based on the limiting reactant. Which is the limiting reactant? Okay, so the hydrogen ion completely reacts with 2.5 millimoles of the hydroxide ion forming 2.5 millimoles of water. So at neutralization, I have no hydrogen ion, I have 0.1 millimole of hydroxide ions, and I have some water, which once again does not affect the pH, so I'm ignoring it. So I need to find the molarity of the OH this time. It's 0.1 millimole over the original 25 milliliters of the acid plus 26 milliliters of the base, and that turns out to be 0.00196 molar. The hydroxide ion concentration is equal to the negative, is equal to 0.00196. pOH is equal to the negative log of that. The pOH is equal to 2.71. So the pH is equal to 11.29. Okay, ladies and gentlemen, I want you to look at the difference here. What is the total volume of solution right here?
Oh, 51. 49 milliliters.
49 milliliters. What's the total volume of the solution here?
That's right.
51 milliliters. Okay, look at the huge, enormous rise in pH when you added 2 milliliters of the titrant of the base. That is this portion of the curve. Just went whoosh all the way up. Good there? Okay. Now I want you to look at this. Stop groaning. And stop that as well. Irritating. Okay, ladies and gentlemen, we're looking at the strong acid, strong base. We know that the equivalence point is 7. I expect you to be able to do a couple of things here. Look at this graph and tell me what the pH is before it starts, or calculate it. If you have to calculate, it's a negative log of the hydrogen ion. Now, please also note that this could have a different form. You could have this graph look like this. Yep. This would be a strong base being titrated with a strong acid. Yeah. The equivalence point is still going to be 7. Okay. You will notice that the pH does not change much until you get to this area, and then you find the equivalence point. The equivalence point is halfway between this high rising slope. All right, got it.
What's the high rising slope?
Why is it so sudden?
Yeah.
Because of the neutralization. All of a sudden you are,
Accidentally pouring a
yeah.
little more.
Well, no.
It just does how locked work. That looks
Okay,
like
in the week, it has to do with how things are being buffered.
Oh.
Oh. Okay. Now, we figured out how to find the pH all through here. This one I'm going to consider we can answer anything we want on this graph. All righty. Now, how many strong acids are there?
6.
How many strong bases are there?
Group 1 and there's a hydroxide.
6, maybe 8, depending on who you talk to. So what do you think the chances that you're always going to do a titration with a strong and a strong?
Not very likely.
Not very likely is the answer. So what you're more likely to find is a weak acid and a strong base.
Like we did.
Let's use our favorite weak acid. When left to its own device, acetic acid will dissociate
A little bit.
based on its Ka into this. Everybody agreed?
Yep.
And when it's all by itself, its pH is totally determined by the hydrogens that dissociate. All right. Now, let's say we take acetic acid and we titrate it with a strong base. Uh-oh. The strong base is totally domineering. It will go over and kidnap that hydrogen ion. It will force the acetic acid to dissociate. As long as there's hydroxide present, free hydroxides, it will take the hydrogen ion, forming acetate and water. Once the hydroxides are gone, acetic acid goes back to its normal, very friendly place and dissociates slightly. Do you understand what I'm saying? You got OH, there is water being formed, and this is dissociating. So, that makes these problems a great deal of fun. Here's why. First of all, there are two steps just like the last one was. To solve these, you're going to do an ICN. And when they ask you to solve for pH, you need to use a rice table. So that's all this is. The only difference between this problem and the last problem is you have a rice table going on. Now, what I would like to show you is this. In real life, here's your strong base, and here's your weak acid, yeah?
Yeah.
Okay. That will make nacho and water. Yes?
Yes.
Okay. All right. Got that in your little brain?
Yes.
Little.
Now let's talk about the point at which the equivalence point happens. What happens when the equivalence point happens?
pH moles equal moles.
Moles of acid.
Moles of acid equals the moles of base. So let's say at the equivalence point we started out with 10 moles of 10 moles of acid. We have 10 moles of base. They're both used up. What do you have here? 10 moles of this. All right. At that point, can you tell me what kind of salt this forms? Yes, I could if I did a little four-square deal. It's
It would be basic.
It's a basic salt. It's a basic salt. So, at the equivalence point, when you have a weak acid and a strong base, the pH at the equivalence point will always be greater than 7 because it's the salt that's determining the pH. Yeah?
Yeah.
Okay, we're good there. Now, I want to direct your attention to a few more things. Right here, what is this?
An acid?
Weak acid.
Weak acid, yeah.
What is this?
No, I know.
It's conjugate base.
It's conjugate base. What did those make?
A buffer?
Uh-huh. Oh, that was so yesterday. Do we have to do buffers again today? Unfortunately, you do, folks. You do.
I love buffers.
Alrighty, my friends. Two things I need to say about that. Okay, the equivalence point to this, if I were to take this down, happens when, I'm going to say, 8, 9, 10, 11 mLs of base has been added. Everybody agree with me?
Yes.
There is this
Yeah.
point when you're halfway to the equivalence point. Here's the equivalence point. How many mLs of NaOH would be halfway?
6.5.
5.5. 1, 2, 3, 4, 5.5.
Okay.
Right there.
6.5 is close enough.
Halfway to the equivalence point. The pH would be approximately
Equal to the K.
1, 2, 3, 4, 5. The pH would approximately be 5. At that point, halfway to the equivalence point, the pH is the same as the pKa. I don't even know what a pKa is. What are you talking about?
Negative log of
Yeah, negative
PA.
Uh-huh. pKa is the negative log of Ka. Could you identify some weak acid if you found out the equivalence point, figured out from the graph half of the volume of the titrant, figured out the pH, figured out the Ka, and bippity boppity boo, you know the acid?
No.
Yes, you could.
Let's do it.
Yes, you could. You will. All right, now,
Is that our next?
why is this so? How come this happens? Okay, let's look at this. We have our weak acid, we have 10 moles of it. Halfway to the equivalent point, we've added 5 moles. We started out with 10, we added 5 moles. What happened to 5 moles? Put it in the box, would you? 5 moles of the weak acid.
Gets made into the right thing.
It's gone, and it's made 5 moles of nacho, hasn't it? Uh-huh. Mm-hmm. So if we looked at our Wonder equation, and then we found the molarity because we're good workers. Halfway to the equivalence point, we have neutralized half the acid, forming half of it, half the conjugate base, yes?
Yeah.
These two things would equal 1, and the hydrogen ion concentration is equal to the Ka, or the pKa is equal to the negative log of the Ka. Get how that works?
Yeah.
All right. So this is a huge, enormous thing to know. That the pH for a weak acid strong base is greater than 7. Halfway to the equivalence point, pH is equal to pKa. All right.
Wait, what?
I just said that.
Why wouldn't the same thing happen when there's like 7 added though? Wouldn't it still cancel out
Okay.
if it wasn't?
If it was strong?
Oh, never mind.
Okay. All right. Now, the weak base strong acid is really the same thing, only it's the reverse mirror image of this. You have the pH is less than 14. It's a weak base. You still have an equivalence point. This time, the equivalence point will be less than 7. Why? Because your weak base is being titrated with a strong acid, forming a salt and water. This salt is acidic. Okay, do you still have halfway to the equivalence point, pH is equal to pKa? Yeah. Yeah. Now, after the equivalence point for both of these graphs, after the equivalence point,
So there's 3.
you keep on pouring in this case, the strong base. The pH is just the negative log of the POH. I mean, is the hydroxide ion concentration, negative log of the hydroxide ions, POH. Then you figure out pH. Boy, did I say that badly. So tomorrow when we do the calculations, we will unbundle you. All right, today we are not doing any calculations for the weak and strong. That is another day. I do want to show you what we will be doing in the lab, and that would be a titration of a polyprotic acid. I remember telling you, you didn't pay any attention, but I do remember telling you that a polyprotic acid dissociates 1 proton at a time. So if we had, let's say these are my axes, we had, here's the equivalence point, 1. All right, we have H3PO4 here. This is that special place where pH is equal to pKa. So we could find the Ka1 there. And then we would have, like in the same beaker, another titration going on.
Are we gonna have to do this question? This exercise 10 question that we're drawing all of them?
No.
All right, good. I'll keep
And
going.
then we would have another. Look, I already read it for you anyway. Here it is.
Snake.
It's a snake. Here it is, right here. Alrighty then. So your first titration, H3PO4 plus OH, is going to make this. Yep. Right here is its equivalent point. Its equivalence point is 50 mLs. So you, being the smart kids that you are, will find half of that, 25 ml. Find the pH, 2.0. Say 10 to the negative 2.0, and you have the Ka for this. That'll be Ka1. You will use methyl orange as the indicator for this. Then you're going to add a little bit of phenolphthalein, and you're going to continue to titrate, continuing adding some NaOH until you hit the second equivalent point. It happens at 100 mLs. Ka2 would be found halfway between 50 and 100, which is 75. That titration would be this. So you find Ka2. We can't do Ka3. Anybody know why?
It's too little.
It is too little. Our pH meters, I mean, we're going to use pH meters, which give us more accuracy, but we just couldn't find the change in pH. It's just too teeny weeny.
So, but obviously you don't have to do calculations, you just look off the graph, right?
You are going to do a very good graph.
Wait, you mean we start with some solution with a pH of 2,
Mm-hmm.
and we'll end up with a solution that have a pH of 13?
Mm-hmm.
I think either one will kill us.
Either one will kill you, so don't drink it.
Oh, so only drinking.